Welcome to all in the lecture series of functional analysis. Now in this lecture we see the theorem related to bounded linear operator. So the first theorem is, if a norm space is finite dimensional, then every linear operator on capital X is bounded. That is we have to show. So we start with a norm space which is finite dimensional. Let capital X be a finite dimensional norm space. Let dimension of capital X equals to n, which is strictly less than infinity. As it is finite dimensional, therefore we consider a base, and here we consider the base e1, e2 up to so and en be a basis for capital X. Then every x belongs to capital X is written as a unique linear combination of the elements e1, e2 up to so and en. And therefore here thus for any small x belongs to capital X has a unique representation. Has a unique representation. X is equals to xi1 e1 plus xi2 e2 up to so and plus xi n en. Has a unique representation as x is equals to xi1 e1 plus xi2 e2 up to so and plus xi n en. It is written as summation I is running from 1 to n xi I e I. Now here we consider norm of Tx. Now here to show that T is a bounded linear operator, that means we have to show that for any x belongs to capital X, we have to show that norm of Tx that is less than or equals to C into norm of X. That is we have to show, and therefore to prove this, here we start with the norm of Tx. And now here we are putting the value of x, that is equals to norm of T of, putting the value of x, that is summation I is running from 1 to n xi I e I. As T is a linear operator, therefore it can be written as norm of summation I is running from 1, it is equals to summation I is running from 1 to n xi I Ti. Now it is less than or equals to summation I is from 1 to n mod of xi I into norm of Ti. That is norm of Tx, that is equals to norm of summation xi I Ti. It is less than or equals to summation I is from 1 to n mod of xi I into norm of Ti. Now for each j, for each we can say that I, and I is between 1 less than or equals to I less than or equals to n, norm of Ti, it is always less than or equals to maximum over I norm of Ti. And therefore here, using this inequality, we can write down this is less than or equals to maximum over I norm of Ti. Now maximum over I Ti, it is always greater than or equals to each term, and as this each term which is less than or equals to this maximum over I norm of Ti, and now this maximum is now independent of this I, because it is nothing but something a fixed real number which is greater than or equals to norm of TEI for each I. That means here norm of TE1, it is less than or equals to maximum over I, norm of TEI. Norm of TE2, that is also less than or equals to this maximum. Norm of TE3, that is also less than or equals to maximum over I, norm of TEI. That means each term is always less than or equals to this maximum, and this maximum is nothing but something of fixed real number, and therefore here it is independent of this I, and therefore we can write down this is less than or equals to maximum over I, norm of TEI into summation i's from 1 to n mod of xi I. That is the norm of Tx is less than or equals to maximum over I, norm of TEI into summation i's from 1 to n mod of xi I. Now here we are giving the equation number 1. Now here we have to apply the lemma. That lemma, the statement of this lemma is, that is the lemma 2.4.1 in the book Introductory Functional Analysis by Irvin Krejcik. That lemma says that let x1, x2 up to so and xn be a linearly independent set of vectors in a norm space capital X, and capital X may be finite dimensional in a norm space capital X, and this X may be finite dimensional or infinite dimensional. Then there is a number C. Then there is a real number C greater than 0 such that for any choice of scalars alpha 1, alpha 2 up to so and alpha n, norm of alpha 1 x1 plus alpha 2 x2 up to so and plus alpha n xn, this is always greater than or equals to C in bracket mod of alpha 1 plus mod of alpha 2 up to so and plus mod of alpha n. Here C is strictly greater than 0. This is the lemma 2.4.1, and now here we have to use this lemma for this summation i's from 1 to n mod of xi I, because here we have to given that in this theorem we have to given that E1, E2 up to so and En, this is a base for capital X. As it is a basis for capital X, that means this set is a linearly independent set of vectors. Now for this linearly independent set of vectors in our space is a norm space, therefore this is a linearly independent set of vectors in a norm space X. Then by using this lemma, there exists a C greater than 0 such that for any scalars alpha 1, alpha 2 up to so and alpha n, here we have norm of alpha 1 x1 plus alpha 2 x2 up to so and plus alpha n xn. Here each xi, it is in this lemma, each xi that is equals to ei, that is our linearly independent set of vectors, and instead of alpha I, here we have each alpha I that is equals to xi I, and we apply this lemma here, and then we get that norm of, now here alpha 1 x1 plus alpha 2 x2, instead of that here we have xi1 e1 plus xi2 e2 up to so and plus xi n en, and that is nothing but, this norm is nothing but, this is equals to our norm of x. This is equals to norm of x, and now by using this lemma it is greater than or equals to C into, now mod of alpha 1 plus mod of alpha 2, instead of that we have mod of xi1 plus mod of xi2 up to so and plus mod of xi n. That means here we have summation i's from 1 to n mod of xi I. And here this C is strictly greater than 0, that means this C is not equals to 0, and therefore we can write down this equation, that is norm of x is greater than or equals to c into summation mod of xi. That is norm of x is greater than or equals to c into summation I from 1 to n mod of xi. This implies that summation I from 1 to n mod of xi, it is less than or equals to 1 by c into norm of x. And therefore here, using this result, that means from equation 1 and 2, we can write down norm of tx, which is less than or equals to maximum over I norm of TEI. And now this summation is less than or equals to 1 by c into norm of x, and therefore into 1 by c into norm of x. We can maximum over I norm of TEI into 1 by c, we give it the name, say gamma, that is equals to gamma into norm of x. That means here we get that is norm of tx, it is less than or equals to gamma into norm of x, where gamma equals to maximum over I norm of TEI. And therefore here we get that norm of tx is less than or equals to gamma into norm of x. This implies that t is a bounded linear operator. And let capital T from script d of t to y be a linear operator where dt is subset of x and x comma y are norm spaces. Then we have to prove the two statement that t is continuous if and only if t is bounded, and another condition is that if t is continuous at a single point, then it is continuous. These two statements we have to prove. That means here we have to given that a linear operator is continuous if and only if it is bounded. It is true where x and y are norm spaces, and here if it is continuous at a single point, then it is continuous. That is we have to show. So firstly we prove the first statement, that is t is continuous if and only if t is bounded. So for that, first of all we take t equals to 0. If we take the t equals to 0, then t is a 0 operator, and the 0 operator, for the 0 operator the first statement is trivial. So here we start with that t not equals to 0. As t not equals to 0, therefore we get that norm of t, that is also not equals to 0. Now here we assume that t is bounded. Assume that capital T from script d of t to y is bounded, and as we consider that t is bounded, therefore we have to show that t is continuous. So we start with any arbitrary point of dt and consider x naught belongs to script d of t, be any arbitrary point of script d of t. Let epsilon greater than 0 be given. We start with any arbitrary epsilon greater than 0. Then for every then for every x belongs to dt such that norm of x minus x0, that is lesser than delta, where we are taking the value of delta equals to epsilon divided by norm of t, we obtain norm of tx minus tx naught. Here we assume that the operator t, that is a linear operator, is bounded, and we start with any point x naught, which is the point of dt. Here we have to show that t is continuous. So we start with any arbitrary point of dt, and we start with epsilon greater than 0, and then for every value of dt such as satisfying the condition that norm of x minus x naught less than delta, where delta equals to epsilon divided by norm of t, we obtain norm of tx minus tx naught. Just we are taking the linearity of capital T here, that is equals to norm of t of x minus x naught. And as here we assume that t is bounded, and therefore as t is bounded, therefore it is less than or equals to norm of t into norm of x minus x naught. But here we know that norm of x minus x naught, that is less than delta, and therefore it is less than norm of t into delta. Now we are putting the value of delta, that is equals to norm of t into the value of delta is epsilon divided by norm of t. This get cancelled, and here we get, that is norm of tx minus tx naught, it is less than epsilon. That means here we get that is for any x naught belongs to dt. We get for a given epsilon greater than 0, there exists delta greater than 0 such that for all x belongs to dt, norm of x minus x naught less than delta implies that norm of tx minus tx naught, that is less than epsilon. And this implies that t is continuous at a point x naught, but x naught be any arbitrary point of dt, and therefore here we get that t is continuous on dt. And hence here we assume that t is bounded, and we are getting that t is continuous. Now conversely, we assume that t is continuous, and we have to show that t is bounded. Conversely, assume that capital T is continuous, as it is continuous, therefore it is continuous at each point, and therefore here we assume that capital T is continuous at an arbitrary point x naught belongs to dt. And therefore as it is true, this implies that for a given epsilon greater than 0, there is delta greater than 0 such that norm of tx minus tx0, it is less than or equals to epsilon for all x belongs to dt whenever satisfying norm of x minus x naught, that is less than or equals to delta. This is the condition for the continuity. As t is continuous at on dt, therefore it is continuous at each point, and therefore for the arbitrary point x naught belongs to dt, here we are applying the definition of the continuity in terms of epsilon delta definition. Now here we take any value y which is non-zero. Consider any y not equals to 0 in dt. This is the element of dt, and set x is equals to x naught plus delta divided by norm of y. We take norm of y in denominator because here we are taking the value y which is non-zero, and therefore its norm is also non-zero, and therefore we can take it in the denominator, and therefore x is equals to x naught plus delta divided by norm of y into y. Then norm of x minus x naught, and that is equals to, it becomes that is equals to norm of delta divided by norm of y into y, but it is a scalar, and therefore here we get that delta divided by norm of y into norm of y, and that is equals to delta. That means in this case we get that norm of x minus x naught, that is equals to delta, that is norm of x minus x naught, that is equals to delta. But when norm of x minus x naught, that is equals to delta, implies that norm of tx minus tx naught, that is less than or equals to epsilon. We give it the equation number 1. Now we consider norm of tx minus tx naught. As t is linear, therefore we can write down it is a norm of t of x minus x naught. But here we are putting the value of x minus x naught, that is equals to norm of x minus x naught is delta capital T of delta divided by norm of y into y. Now delta divided by norm of y, it is a scalar and t is linear, therefore it is equals to norm of delta divided by norm of y into ty. Now we can write down it is equals to, now here delta is positive, norm of y is also positive, and therefore it is equals to delta divided by norm of y into norm of ty. Now as that is norm of tx minus tx0, that is equals to, we get here that is norm of tx minus tx0, that is equals to delta divided by norm of y into norm of ty. But here norm of tx minus tx0, that is lesser than epsilon, and therefore it is also less than or equals to epsilon, and this implies that norm of ty, it is less than or equals to epsilon divided by delta into norm of y. If we are putting epsilon divided by delta equals to c, that means here we get that c into norm of y. That means we get here that is norm of ty, it is less than or equals to c into norm of y, where c equals to epsilon divided by delta, which is strictly greater than 0. In this way we get that norm of ty is less than or equals to c into norm of y, and this implies that the operator capital T is bounded. We start with that capital T is continuous, and we are getting that T is bounded, and hence in both the parts we get that T is continuous if and only if T is bounded. Now we have to prove the second statement, that if T is continuous at a single point, then it is continuous on that set. That is, we have to show that. Now here continuity of T at a point implies the boundedness of capital T, as we just prove, because here we prove that we start with T is continuous, and therefore it is continuous at that means we say that it is continuous at any point x naught belongs to dt, and then it is continuous at x naught belongs to dt, and therefore using this we prove that T is bounded. We prove that capital T is bounded. That means here if T is continuous at a single point, then it is bounded, and boundedness implies that T is continuous, and therefore in this way we get that if T is continuous at a single point, then T is continuous, if T is continuous at a single point, then T is bounded, and the boundedness implies again continuity from the first statement, and in this way we prove the second part of the theorem.